Okay, welcome to some Chapter 3 material on checking for constancy of variances. I have 4 data sets that I'm going to go through and jump, and it's all related to checking via the homogeneity of variances or unequal variances within jump. So let me start with this first one. What's in parentheses here are the file names that I need to pull up within jump. So first guy is variance homogeneity example. I have a constructed example with 10 x's, 5 of them are 1s, 5 are 5s. The true y is 5 plus 10x, usual friend. I have sigma rig to be 1 for when x is 1 and 10 for when x is 5. I have normal errors, random normal, so normal 0, 1. And what's observed is the y true plus sigma times the error term. And then this column is the same as the x column, except that it's given as a nominal. If you look over here, it's the red histogram, means not nominal. X blue is a triangle, is continuous. So let's fit it and pull up the residuals, and then we'll check the residuals. This is the simplest possible case. Analyze fit y by x. X is a factor. Y observed. Run it. Fit the line. Make the markers bigger. You can see that there's a bigger spread out here at x equals 5 than here. I need to save the residuals, but for a change, let me also save the predicted, so in case that's unclear to people. Save the predicted. Oops. Save the predicted and save the residuals. So back to the data sheet, I've managed to then add a couple of columns. Our predicted y observed and the residuals for y observed. So notice there's just a single prediction at value x, 15.234, and then what was observed on the first value of x was 15.88. So yi observed minus y predicted, yi minus y hat, 0.64. 13.88 minus 15.23 minus 1.35. The predicteds are all the same at that individual x, and a different prediction down here, and likewise that's where we get the residuals. So we saw from the graph that the residuals were different. Let's check them using unequal variances. So we'll do fit y by x, where this is y, this column is y, and this column is x. You need this as a categorical in order to pull up unequal variances. So put the residuals as the y, nominal x as the x factor, run, and then here again you can see the points laid out. And then you go to unequal variances for the test. And here we have it, as expected. Here's the test down here. Bartlett, highly significant. Levine, low p-value. The Brown-Forsyth, looking at the absolute deviations from the group median. So the group median at x equal 1 is around 0. Over here, this is the group median. So we can see that it definitely rejects. And if you happen to forget what tests are what, go into the tools help, put the question mark, and jump will kindly provide you excellent description of which test is which, and this is the test that we've preferred since basically 1981. So this is the test that I tend to recommend most commonly. So this is a simple case. This doesn't look other than the regression context. You could have just had data, 2 groups of data, and run this kind of test. So that's a simple example. Let's do another one that's just a little bit more complicated with 4 levels. 4 levels of x, just to remind you. 4 levels of x, and here's the data file. So we're going to go with, instead of 2 levels, 4 levels, or 4 groupings of x. Here I have x as 1, 5, 9, or 13. Y true, in practice you would know it, 5 plus 10x, our old friend. And then I have it configured to do two different data sets depending on the sigmas chosen. High, low, low, high for 5, 1, 1, 5 for the sigmas at the 4 different levels of x. 1, 5, 5, 1 for the 4 different levels of x, meaning low, high, high, low. And here the error is again normal 0, 1. Makes it easier to reproduce the results later. And then here's the observed y's. True value plus sigma times the error, and it's labeled accordingly to line up. So again, we need to do fits to pull up the residuals, and then we can check to see whether our tests are able to pick up this case where the variances are indeed unequal. The sigmas are unequal, therefore the variances are unequal. So I'll fit y by x, fit both y's at the same time, x continuous. Do a fit for each, holding down the command key on my Mac, fit line, and then holding down the command key to save the residuals. Since I saved predicteds on the other ones, I don't think I need to do that yet again. And it looks like in the background we got both of them, both sets of residuals. Oh, great, I did predicted. Oh, I'm sorry, I did the wrong. Here we go. Here are my two columns of residuals. We like to test whether the variances are equal within these groups, and since we have 4 groups, we'll basically get 4 groups here. And I have x as a nominal column, so analyze, fit y by x, my 2 sets of residuals against x nominal. Make the symbols bigger. So clearly the one on the left had big sigmas on the edge, smaller ones in the middle. This case, low, high, high, low, small residuals, more spread out. So let's get the unequal variances values, tests, results. So what do we have here for the one on the left-hand side? P-values for all of them are fairly small. Brown-Forsyth, 0.0104. Levine's a little smaller. Bartlett's the smallest of all. Of course, I started with normal errors, so under that circumstance, Bartlett's test is appropriate. If we had other error terms, which is what we encounter in practice, where we wouldn't be able to rig it this way, not the case that Bartlett's looks like it has the best p-value in terms of rejecting. Over here on this side, here's the fits. Again, all of them reject, which is comforting, and this right-hand side compared to the left-hand side where the high variability is in the middle, so happened that the p-values were a bit higher here. You can see that it depends on how the fit works out. So it's not going to we have basically 2 different fits. So that's set up. What was the next one? Take the Toluca data that we've been dealing since with Chapter 1, and here the data is not naturally arranged in 4 groups of equal sizes. It's scattered depending on the number of lots. So let me run that example. The Toluca sorted by lot. So it's the original data file, but notice lots going 20, 30, down to 120. Same original data, I just resorted the table by lots, and then everything else got sorted accordingly. I've already done the fit for hours on lots and saved the residuals. I guess I might as well do a double check here. Hours for a certain number of lots. Fit a line. Save the residuals. Same values. Oh, slightly different. Oh, I've excluded. Oh, that was worth doing. I've excluded, forgot about this, I excluded these 3 rows for purposes of doing the variance homogeneity test, so it did the fit on the rest of the data. So that's why these residuals, of course, they're missing in here. let's go ahead and clear row states and verify that these are the residuals I would want corresponding to the full data set. You wouldn't do it on a subset. So again, analyze fit y by x, hours, lots. Okay, fit a line, save the residuals. And here I do indeed have these values over here, which I just did the fit on, are matching this column here that I already had built into the file. So let's proceed with those. So these are the residuals of interest. Here they're repeated, so I guess I can get rid of this column just to get it out of the way. Delete it. Now I have various groupings. There's subsets of the data. So let's see, and for lots, so these are my groupings, group 1 through group 4. Notice they're all with the red triangle. So these are our allocations. Let's just have a look at the residuals. Let's see what happens. Let's see what happens with just run it, analyze, fit y by x, and my residuals as a function of these different groupings. Guess I didn't really need to necessarily exclude those rows. That was for something else I was up to. And oops. Make the marker size bigger and check for unequal variances. Again, I'm holding the broadcast key so it does them all. So here's the group 4 and 3. All the p-values are insignificant regardless of the test. Here it is for 6 and 5, so I'm moving in. Here's for 9 and 9, the smallest 9, the largest 9. And here's 10 and 12. Again, nothing too exciting. So for the Toluca data set, regardless of how I did those kind of groupings, I did not see inequality of variances. And that's confirmed actually graphically as well. So that was the Toluca. And finally, the GPA-ACT test data set. Again, I have a bunch of combinations of them here. Pull them up. Get rid of some of these files here while I'm at it. GPA data set. Okay, here I have original row. I've sorted them by ACT, the ACT column. Move it back to the top. Starting at 14, moving up, there's a bunch of repeats. And as I've done before, I've kind of have these groupings. Group 1 has one edge, Group 2 has a little bit more, Group 3, Group 4, Group 5. There's 120 rows here, so it's hard to show it all. And I actually also went back and did the first 5 smallest, corresponding to the smallest ACT scores, and also the 7 largest, which is down at the bottom of the file. So I have 120 rows, nothing's excluded. I'm leaving in those 2 knuckleheads that we mentioned previously that had very respectable ACT scores and pitiful freshman GPAs. So let's get the residuals. ACT is the factor, GPA is the y variable. I kind of like screening. This is standard least squares, that's the one I want. Rather than one of these other ones, there's plenty of other choices. Let her rip. And now I want to save residuals. Save columns. See this, when you get into fit model, there's all kinds of other stuff you can store. Store the residuals. Okay. I don't think I'll need this anymore. I think this is the same old fit we've had. It's a horrible fit, 0.07. Yeah. Intercept is significant. I mean, the slope value is significant, but it's not practically of interest. I could have also, let's just double check, fit y by x, make sure I didn't do anything wrong. ACT, GPA, let her run, fit line, save residuals. They line up, of course. All right, no problem. So now we have our residuals from our fit y by x. Let's see how the tests for homogeneity variances come out. Let's see, do I have ACT as, oh, I'm using the groups, so that's how I'm doing it. I already have it set up appropriately. So analyze fit y by x, my residual column, all these different groups. Okay. And check for equivariance. I got my broadcast key down to do them all at once. So again, we can tell by the count numbers how much. So the 12 smallest ACT scores, the 11 largest. No difference. Nothing significant. All pass. P-value low, null must go. P-value's high, so no evidence here of unequal variances. Also see it by this graphically. Really doesn't look like much of a difference. The standard deviations themselves are like, here's one, 0.67, 0.85. P-values are not too exciting. This is with 34 and 35, 43 and 45, over 2/3 of the data. Here's 55 and 55, just excluding the middle category, which hard to say which side it would be in. And then finally, I also happen to do just the very extreme, the first 5 and the last 7. And here, with the small sample sizes, we do see some p-values that are significant. It's very slight evidence, but such a small part of the data, it's almost as if we've gone on a fishing expedition here, looking back at our plot. Let's see here. Oh, that guy. We're dealing with the points that are really at the edge. Here's these 3, 4, those 7 to the right, these 5 over here. Is that enough to substantiate a big difference? Well, our saving grace, as I mentioned in class, is the R-square is so low, we're kind of fussing over an assumption in a situation where we wouldn't find this model compelling anyway. It would be, this is tantamount to saying, if with our original data set, let me show you one thing here, tables, summary. If we look at the range of the residuals by ACT score, here are the range of the residuals across ACT values, and I could kind of look down here and say, yeah, why don't I test, say when ACT is 29, that had a 3.456 range, which probably corresponds to a fairly large standard deviation, versus here's one that's 0.89. So if I just cherry pick those two, that might be significant, but that's really not appropriate. And I should be altering the alpha level in the spirit of Bonferroni, which we'll talk about a bit in chapter 4. So let me stop there.